Hello everyone, and welcome to the Newton's second law pre-lab, part 2. So in this half of the lab, we're going to use a different independent variable, the mass, measure the resulting acceleration, and keep the force constant. So this is acceleration versus mass with constant force. And again, we're going to use our old friend, the modified Atwood's machine. Now remember here, A is the cart, right? So MA is the cart mass. B is what we call the hanging mass. And these two together make up what we would call the system mass if we look at it as a system. And that's the way we're going to do this part of the lab. So we're going to look at it a little differently. Part 1, we focused on what was going on with the cart. Okay, but for reasons of controlling variables, we can't really do that for this half of the lab. So instead, we're going to turn this into a system. You might remember doing this a couple of units ago. Here's my system diagram. The little dotted line represents the system boundary. You notice that I've kind of gotten rid of the string and the massless frictionless pulley, and all of that is just kind of inside of the system and disappears. So I've taken B and I've slid it up next to A. Okay? And then we're going to look at this as one big system, or if you will, one big system mass. So let's draw the force diagram here. What forces act on this system? Well, of course, gravity, right? Except we've got two forces of gravity. We've got a force of gravity that acts on cart A, down, right? Which I'll call F of G A. The extra subscript tells me this is the weight of A, which is the cart. And then there's a force of gravity on B. Now, in reality, the force of gravity on B, of course, pulls straight down. Gravity always pulls towards the center of the Earth. But that's not how I did my diagram. Do you see how I slid B up to the side to look at it as if it was one big object, not two separate objects tied together by a string over a massless frictionless pulley? So in my diagram, what direction would I draw that force? I draw it out to the right. So this is F of GB. Okay, this is just the weight of the hanging mass. Okay. Now, cart A is being supported by the track, so that would be a normal force. And the normal force and F of GA are going to balance, and I know that because A is going to move horizontally, it's not going to move vertically, which means it's not accelerating vertically, right? If we use our new terminology, right? And this is basically Newton's first law. If there's no acceleration, the forces have to balance. The net force has to be zero. But this is just vertically, okay? So these two cancel out. Now remember, there's no friction, there's no angle to the track because I balanced those out, hopefully as well as can be done. Please don't mess with the tracks. So then the question becomes, well, what is providing the net force in this case when we look at it as a system? When we just looked at the cart, it was the tension in the string. But the tension in the string is kind of lost to us here because we're looking at it as one big object. Right? So look at our force diagram. That's why we drew it. What force is unbalanced? What's causing the net force? Do you see it? Yeah. It's the force of gravity on B. It's the weight of the hanging masses. Right? The force of gravity on the hanging masses. And hopefully you know how to calculate the force of gravity on some mass near the surface of the Earth. You take the mass and you multiply it by the gravitational field strength. So our net force in this part of the lab, looking at it as a system, is the force of gravity acting on the hanging mass, which is just the hanging mass times 9.8. Right? Hanging mass in kilograms, so it's 9.8 newtons per kilogram. So that leads us to how we're going to keep the force constant. Right? If we want to keep this net force constant, that means basically we need to keep the hanging mass constant. Remember how that's what we changed in the first part of the lab? Right, so this time we're going to leave what's on the end of the string the same the whole time. And it says this on your lab sheet, but I'd like you to put 100 grams onto the end of the string. With the 5-gram mass hanger, that's a total hanging mass of 105 grams, or 0.105 kilograms. And you're not going to change it throughout this whole half of the lab, okay? So you're going to put the 105 on the end of the string, 100 plus the mass hanger, and then you're going to leave it there the whole time, and that will keep the force constant. So then we want to change the mass, right? So if we're not going to change what's on the end of the string, how are we going to change the mass? Well, we're going to put masses onto the cart, right? And thereby change the system mass, if you will. Okay, now we can measure the acceleration of this entire system just by measuring the acceleration in the cart, because after all, they're tied together by a string, right? They're moving together like one big thing. And we can do that just like we did in the first half of the lab. We can use the little encoder wheel on the bottom, get a velocity time graph. The slope of that graph is the acceleration, right? So same technique you've used in the last couple of labs. Now, this is where we have to be careful. When it comes to recording the mass in your data table that you're using, we can't just use the cart or the stuff hanging on the cart, because this net force is accelerating both masses, right? They're both being accelerated. This is the force that acts on both, right? To tow it, if you will. So we have to use the system mass here, okay? And this is a little tricky. So how are we going to calculate that? Well, you're going to take the mass of your cart. There's an electronic balance in the back of the room. You can figure out what that is. It's around 275 or 0.275, give or take. You're going to put a couple of black bar masses in your carts, and that's just to slow things down. They're about 500 grams a piece, or 1 kilogram. And from time to time, you're going to add masses, okay? And those are those little masses, and it depends how many of them you add, all right? And don't forget, you got the 105 or the 0.105 hanging off the side. So you got to add all these things together every trial to figure out what your system mass is. And you're going to change this one, right? The added masses every single time, which changes the system mass. Okay? So this is one of the big errors in this lab, is that people put like the mass of the cart or the ones they add to the cart. They don't put the entire system mass in there. Okay? And this equation is on your lab sheet right above the data table to help you out. Okay? Like I said, you're going to put these two big black bar masses, which are about 500 grams or for about a 1 kilogram total, in the cart for this half of the lab. And the only reason you're putting them in there is to slow everything down, all right, so it doesn't fly around on you. You're going to do your first trial with no additional masses on the cart. Yes, you're still going to have the black bar masses in there the whole time, but you're not going to put any other masses in there. You'll run your trial, you'll measure your acceleration, you'll calculate your system mass. And then every successive trial, you're going to change the system mass by placing one of those little aluminum masses in the slots on the side of the carts, right? Each one of those little aluminum masses is about 125 grams, or an extra 0.125 kilograms. So you'll run a trial with just one of them added, then two of them added, then three of them added, then four of them added. And those are all your trials. That's how you're going to change the system mass. And again, remember to record the system mass. That's what you're going to graph, not the individual masses, because this force accelerates the entire system. Now, this one's a little trickier than part one, which is why I did it second, in that you are not going to get a linear graph here when you graph acceleration versus system mass. You're going to get a different shape. In fact, you're going to get a shape we haven't seen yet, a new relationship. And when we don't get a linear graph, what do? We linearize it. And we're going to linearize it by doing something to the system mass. And that something is, you got three choices, right, on that graphical analysis sheet. You can either square it, you can square root it, or you can invert it. Invert means 1 over the system mass. Now, hopefully, if you think about the relationship, you'll be able to decide which one of these three should work, right, and try it. If all else fails, you can always guess and check and just run through the three till you find one that works. But, you know, that's not the best way to do this. We want to think, right? If you're not sure and you can't get it to linearize, call me over, right? And I bet in just a couple of questions, I can get you to see why or what you need to do to the system mass to turn this into a linear graph, right? Follow the steps on your lab sheet. Follow the graphical analysis help sheet that we've used before, right? And that'll help you do both. And then eventually you're going to call me over to look at it. You're going to put a slope into the Google file, right? Google form to collect it so that we can look at it in the post lab. And please, only one for each lab group, right? I don't need, if you have 4 people in your lab group, don't enter it 4 times, right? Just enter it once for your lab group, please. That's good enough. Okay, and you got some questions to answer and all that stuff. Please call me over if you're not sure and you really need to follow the steps on the lab sheet to get everything set up and then to run this part correctly. So enjoy part 2 of the Newton's second law lab.